Welcome back to AP Chemistry with Mrs. Mays. Today we're working on VSPER theory. VSPER theory is how we are able to predict molecular geometry. It's valence shell electron pair repulsion. So basically we start with a Lewis structure, which tells us how the atoms are connected to one another, but it doesn't tell us anything about the shape or the geometry of the molecule itself. And honestly, the shape is going to have a big influence on the properties of the molecule itself, how it reacts with other things and its physical properties as well. So we start by drawing the Lewis structure of the molecule. When that's done, we'll count the groups of electrons, those that are bonding or non-bonding. We call these electron domains. So we decide what the electron domain geometry is based on all the repulsions between the electrons in their different locations around the central atom. And then once we know where the electrons are, we decide on the molecular geometry, which is based on where the atoms are. Because the electron domain geometry predicts where all the electrons will be, but not all of the electrons will be in bonds. If they're just lone pair electrons, then they seem invisible. But a place where an atom is located is not invisible. So the molecular geometry won't always match electron domain geometry. And because there are some lone pairs, angles can be decreased slightly if these lone pair electrons cause squishing or crowding of any bonding pairs. The number of bonding pairs of electrons are going to determine some important factors, such as the bond angles between atoms and the underlying structure of the molecule itself. The number of non-bonding pairs, however, the lone pair electrons, are going to help us to decide the actual molecular shape and the actual bond angle between the atoms. So let's have a look at what we mean by this. Suppose you have a molecule with two electron pairs. These bond angles are 180 degrees. The underlying shape would be linear. If you have three electron pairs, then the way to arrange that around a central atom is in angles of 120 degrees, evenly distributed, and that would have a trigonal-planar shape. If there are four electron pairs around your central atom, then that has a tetrahedral shape, and this number 109.5 is going to be really important for many of the molecules that we work with most commonly, like water and ammonia and methane. Then if there are 5 electron pairs, then you very likely have an atom in the center that's exceeded the octet, so you have trigonal bipyramidal, or 6 would give you the octagon. We use this chart to help us predict the shapes, because if you have only bonding pairs of electrons and no lone pairs of electrons, then it's pretty straightforward. That would be this row along here. So you have the linear shapes, the trigonal-planar shapes, and then the tetrahedral shapes. On the other hand, when we add a lone pair, it changes the angle of the bonds. So in this tetrahedral structure, the bond angle is 109.5. But now if we put a lone pair of electrons here, then it takes up more space and pushes these bonding pairs out of the way and changes the bond angle between these atoms. Instead of being 109.5, now this bond angle is only 107. And then if we put in 2 lone pairs of electrons, now it's being squished from both sides, and these bonding pairs reduce the bond angle. The lone pairs reduce the bond angle between the bonding pairs of electrons from 109.5 to 104.5. And then, of course, if we have 3 lone pairs, then you have only 2 electrons that are trapped in a bond here, and the only bond angle you can have between two atoms is 180. So that's how a lone pair might influence the bond angle. It's going to reduce that angle somewhat. You do need to know that this angle is 120 degrees, but you don't have to know how much this angle is going to be. You just need to know that this lone pair is going to squish it. It's just going to be something less than 120 degrees. And so if you say that angle is less than 120 degrees because of the lone pair reducing the bond angle, then you'll be in good shape. You don't have to memorize all of the angles there are. Now let's look at the expanded octet. From the tetrahedral, we know the tetrahedral shape fills in all 4 electron domains around the central atom so that you would have an octet. If you have 5 or 6 electron domains, then you're looking at the types of molecules that have an expanded octet, where they're hypervalent. That occurs anywhere below row 3 where you have access to d orbitals. But d orbitals are not entirely filled in yet. Things like sulfur and phosphorus tend to do this. Xenon is one that's typically used as an example because it can have more than just 8 electrons around it. So if you had 5, you'd be looking at the trigonal bipyramidal shape like we built with our balloons in balloon geometry. But then if you were to take one of those away and just have a lone pair rather than an atom, then it's called the seesaw shape. See, here's the fulcrum and then the teeter-totter. And so that's what makes that seesaw shape. A distorted tetrahedron gets pushed out of the way by those lone pairs. The octahedral shape is with 6 bonded pairs. But if we were to take some of those away, you might get square pyramidal. Take 2 away and you would get a square planar molecule. And take 3 away, have 3 lone pair electrons around this, and you would get the T-shaped. So it's important to know how to draw the Lewis structure first so that we can use the Lewis structure to predict the molecular geometry, and then that's going to affect whether or not we consider that molecule to be polar or nonpolar. What if there is no central atom? Well, there are some molecules where this is true, where they're so complicated that there's not a single atom in the center. Like this one I think is caffeine, I believe. So we could predict the molecule geometry of each angle and build it one piece at a time. For example, this carbon that's labeled number 2 is going to have a tetrahedral shape because it has 4 pairs that are bonding to it in 4 electron domains. But this nitrogen is going to not follow the 109.5 degrees of the tetrahedral because of the lone pairs here. Then we would say the electron domain is tetrahedral, but the molecular geometry is such that it is trigonal pyramidal, which is pretty typical for that nitrogen because of the lone pair there. It has 3 bonding pairs and 1 non-bonding pair, so trigonal pyramidal is the shape in that section. And then you have your carbon with 3 bonds, and those 3 bonds have 3 electron domains, so this particular carbon would have bond angles of 120 degrees because this follows the trigonal planar geometry. So you have to look at each piece of that molecule, and I'm not going to walk us through all of the bits of the molecule. We would just build it one piece at a time as we go to describe its geometry, and its functionality in that region is affected by its geometry. Now there will be exceptions to our predictions because lone pairs take up more space than bonding pairs, and bigger atoms take up more space than smaller atoms. We would predict this tetrahedral to be 109.5, but because of these 2 chlorines on this atom, they're going to squish just about as much as a lone pair squishes it to make that true angle about 107. So the VSPER theory relies on the formation of hybrid orbitals, which describes an overlap of atomic orbitals to form molecular orbitals. So here I've shown the orbital diagrams for our noble gases. And you'll recall that atoms react with other atoms so that they can have the configuration of a noble gas. So in this example, we have two hydrogen atoms that overlap their orbitals so that they can become more stable. That's why bonds form between atoms, to get to the lowest possible energy. And we know the lowest energy state would be the energy state of completely filled orbitals, just like the helium atom here has. So if we had two hydrogen atoms that overlap their atomic orbital structure, their atomic orbital regions, then they can attain the noble gas configuration of helium. And that's why hydrogen, as an element, is a diatomic molecule. They don't hang out by themselves. It's a lot less stable than the two atoms hanging out together. Ionic bonds, on the other hand, are formed by the transfer of electrons from a metal to a nonmetal. So let's look at our most famous example. Sodium and chlorine react to form sodium chloride. Notice this lonely electron in the 3s needs to find a home, and the 3p orbital of chlorine has a place for that electron to go. So we move it over, and now both atoms have noble gas configuration. The sodium ion looks like neon, and the chloride ion looks much more like argon's configuration. So that reaction was stabilized because of the formation of the noble gas configuration. Nonmetals bond by the sharing of electrons. So we can see how the chlorine here is going to partner up with this chlorine electron. One goes up, one goes down. Then they can overlap and share that orbital space, and that would stabilize both atoms. So hybrid orbitals are the overlap of atomic orbitals where the electrons are going to be transferred or shared. So when two orbitals directly overlap, it forms a sigma bond, or a bond between the internuclear axis. In other words, the overlap occurs between the two nuclei of the atoms that are reacting together. So you could get this by having two s orbitals overlap with one another, or you could have an s that's overlapping with the lobe of a p orbital, right here in between. So you form sigma bonds between s's and p's as long as they're on the internuclear axis. Let's look at this online. So here's the joining of two s orbitals to form a hydrogen molecule, H2. Notice how the two s orbitals seem to merge together, and this is what we call a hybrid orbital now, because it's putting two orbitals together so that the electron doesn't just go around one atom or the other atom, but rather it's anywhere in this space. Wow, in that scribble space. That's what this sigma bond looks like. Now we can form other sigma bonds too. Let's look at the sigma bond between two p orbitals. So in nitrogen, this sigma bond forms when a p orbital and another p orbital merge together along the internuclear axis. So those red lobes of the p orbitals are joining together to make a hybrid orbital. In other words, an orbital formed by two different atomic orbitals. So you can have an s with a p, or a p orbital with a p orbital. When two p orbitals overlap, though, perpendicularly, then the overlap is rather side to side instead of directly between the internuclear axis. So it's called, in that case, a pi bond rather than a sigma bond. Let's have a look at the pi bond. So watch the two p orbitals interact side by side instead of directly on. So you get both of the lobes, the red lobe and the blue lobe, merging together, and that's forming the pi bond. So the first bond that forms is a sigma bond. So we usually call that a single bond. And then if you form a pi bond, that's the next bond that's going to emerge, and well, they don't go in order like, hey, you first and then me, But when a double bond forms, you'll have both a sigma and a pi because you're overlapping in both regions, the internuclear axis and the perpendicular axis, both. So if we were going to draw orbital diagrams for molecules, then it might look something like this. So here's one fluorine orbital diagram, and we'll put that together with another orbital diagram for fluorine, and you can see where the hybrid orbital is going to form, where these two regions in space merge together, and that's going to form a single bond, so we would call that a sigma bond, because they're going to join along the internuclear axis between two fluorines. Now let's look at the orbital diagram for oxygen, and you can see now where the hydrogens need to go to fill in the empty spaces in the orbitals. We need another electron right here and another electron right here. So we can merge those two atomic orbitals into molecular orbitals and make water. Oxygen and two hydrogens. Now let's look at lithium fluoride, which we would suspect a metal reacting with a nonmetal. How is this going to work? Right, transfer the electron over, and then the lithium forms a positive ion, fluoride forms a negative ion, and it's ionic because you have a metal reacting with a nonmetal, and that electron's completely transferred over. So let's explore how the orbitals interact.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The three p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce two hybrid orbitals called sp, pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces three equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all three p orbitals results in formation of four equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron. Let's apply the concept of hybridization to ammonia. Here is the Lewis structure for ammonia. There are four electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. This shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the fourth sp3 hybrid orbital.
So in ammonia, we saw the sp3 hybrid orbital because it occupies the tetrahedral shape. So we had 4 electron domains. How do we get 4 electron domains? Well, first you have the s, and then you need how many p's? S holds 1, and then the p has to hold the rest. It can only have 3 different shapes of p orbitals, right? So if you have sp3, that gives you 4 electron domains, and then one of those is occupied by a lone pair. The others are occupied by bonding pairs. So we know this is going to be trigonal pyramidal because that's the shape that results when there are 3 bonding pairs and 1 non-bonding pair. So we'll find it on the chart. Here's my tetrahedral shape. Here's 4 electron domains. We have 1 non-bonding pair. Therefore, the shape is called trigonal pyramidal, and the bond angle is going to be less than 109.5 because these electrons here squish or crowd the bonding pairs into a smaller angle, about 107 degrees. Now let's look at the double bond and the triple bond. Those would be made up by a sigma bond and a pi bond both. So in the ethene structure, for instance, you would have two carbons together with a double bond. In this case, one of them is a sigma bond that lines up along the internuclear axis. The other one is going to be a pi bond that lines up perpendicular to the internuclear axis, where the p orbitals that are above and below the internuclear axis would merge together like this. That's making the pi bond. But don't forget, you also have the sigma bonds, or the single bonds, between all of the carbons and hydrogens. Hydrogen can't form multiple bonds, so we know right along in here is a sigma bond, and along in here is another sigma bond, and a sigma bond here, and a sigma bond here. There's only one pi bond. All of the rest of these are sigma bonds. In a triple bond, however, you would have a one sigma bond available, and then you would have two pi bonds. So let's say in HCN, for instance, we'd have a sigma bond to start off here, and a sigma bond here. They look like sixes. Sorry, that's the sigma letter. Yeah. And then a lone pair. They don't get to be in the hybrid. Then we've run out of sigma bonds. We have to make pi bonds here and another pi bond here. So two pi bonds and two sigma bonds exist in the HCN. 1, 2, 3, 4, 5 sigma bonds and one pi bond in the ethene. So that's how we would work with the VSPER theory and the idea of hybrid orbitals, hybridization, and then sigma bonds and pi bonds when we form bonding orbitals. Let's take another look at this molecule. The dichloromethane would be the name of this molecule. Dichloromethane meaning a methane molecule where two of the hydrogens have been replaced by chlorine atoms. So we would predict with 4 bonding domains, 4 electron domains, and 4 bonding domains that this is going to follow the tetrahedral structure, and indeed it closely does, except that of course the chlorines are taking up more space and squishing the bond angle for the chlorine and hydrogen. But what's important here to recognize is that we have the S with one place where they can overlap, and then 3 places where the P's have to overlap, sp3. That's the hybridization that goes along with the tetrahedral structure, because you get 4 domains for those electrons. Now let's look at another molecule where we said there's not 4 domains. This one had only 3 electron domains and 3 bonding pairs. So we have the S overlap forming our first bond, and then we have to overlap with p orbitals in 2 places instead of in 3 places. So sp2 hybridization is typically associated with a trigonal planar shape because it's formed when 3 different bonds overlap in those 3 different regions. So the hybridization is called sp2. And then if you just had an S and a P overlapping, then we would call that sp1. And I can't see any place where that might be happening, so we'll have to look for that one somewhere else. Notice too, we could locate some pi bonds. Any place where you have double bonds or triple bonds, you have pi bonding occurring, because you have to go not just in a straight-on shot in between the nuclei, but that's going to require then the perpendicular overlap of the p orbitals as well. So we're going to practice describing the types of bonds between atoms and the geometry that results in the molecules. Come to class and be ready to talk about sigma bonds, pi bonds, and sp3 hybridized orbitals. See you guys soon.